We're broadcasting, and we're just going to talk a little bit about the Bohr model of the atom. So we've gone from this idea that atoms are these big, hard billiard balls to the idea that there are particles within the atoms. And then suddenly we started to move into this quantum world. And so things where we thought light was actually a wave, now we're starting to think of it as a discrete set of particles or having wave and particle nature. Now, we also looked down at the Rutherford atom. And so in the Thomson model of the atom, they called it the Raisin-Bun model, where we had like all this positive charge and maybe some of these small electrons, subatomic particles embedded in that positive charge. Then we came up with the Rutherford model of the atom, where we had all of the positive charge compressed in this dense central core. So that was the Rutherford contribution, shooting those alpha particles or those helium nuclei at the gold foil, watching them scatter, some of them being scattered back at a very low rate, most of them passing through. The problem with this idea of the Rutherford atom being discrete particles of electrons surrounding a positive nucleus was that that atom should in fact just explode, shouldn't exist. Okay, there was no way that you could keep a negative electron and a positive proton with the amount of charge that they had apart from each other. If you use sort of this solar system model of the electron orbiting the positive charge, those electrons should radiate their energy, their kinetic energy as electromagnetic radiation almost immediately and spiral down into this positive nucleus, and the atom should explode horribly. So we needed to modify this model of the atom, and this is where quantum theory started to come into play. So the person who did most of the work in moving the atomic model into the quantum model was Niels Bohr. So the experimental evidence for the Bohr model was almost all based around this idea of spectrum or a spectra of light. So, I don't know, can we do this? Okay. And so specifically the emission spectrum. Now, yesterday we were looking at black body radiation. And in black body radiation, it's the idea that something with a temperature will radiate light, and it will radiate quite a broad spectrum of light. We talked about the limitations of that yesterday. Nonetheless, here is light emission by the excitation of particles. And so I don't know if you can see that or not. This is hydrogen. If you were to break that spectrum apart, you would see very discrete spectral lines. You would see very discrete emission lines in different places of the spectrum. So not like a black body, this has very discrete emission lines. Similarly, if we had a broad spectrum of light being emitted from something like a star, and there was hydrogen gas in the way, the hydrogen gas would be absorbing energy, and we would get absorption lines. If you were able to look at this, though, these would be producing emission lines. So the Bohr model is based on a lot of the evidence that we obtained from spectra. So what did Bohr do that was a little bit different? Well, now we're thinking that photons are actually discrete particles that carry discrete amounts of energy. And when a photon happens to encounter an electron, so the hydrogen model of the atom was actually the one that Bohr was successful in making his predictions about. When a photon encounters an electron, that electron can accept only discrete quantities of energy. So only a very specific wavelength corresponding to a very discrete amount of energy can be absorbed by that electron, and the electron jumps to a very specific higher energy level or a higher level shell. So in this case, we have the first shell, n equals to 1. The electron's absorbing a photon. It becomes excited and jumps up to n equals 3. Okay, so that photon's been taken out of the picture. The electron now has a higher level of energy. It can only accept a discrete level of energy. In this case, it's jumped from n equals 1 to n equals 3. Now that electron will only remain excited for a short period of time, and then it has to return to one of the lower energy levels. When it does that, it's going to emit, once again, a discrete quanta of light that will correlate with one specific color of light. So when it does this, now it's going to emit a photon. The photon going from n equals 3 to n equals 2 will be less energetic than the photon that was absorbed, taking it from n equals 1 to n equals 3. Okay? Then this electron might make its last drop to the lower shell, and once again, it will emit a discrete quantum of energy in the manner of a photon, and it's just, it'll be, once again, a less energetic photon than the one that originally excited the particle. So that was Bohr's contribution. He identified that the atom is actually a quantum mechanical object. So it doesn't follow any of the rules of classical mechanics. And Bohr famously said, if you really think you understand quantum mechanics, it means that you don't understand it. So we shouldn't be able to understand really how these electrons work. They're not little balls. And in fact, we start to see them as waves surrounding an atom. So our model of the atom has moved from the billiard ball model to this quantum mechanical model. And that's where we are today. So that's Bohr's contribution. All right. Any questions?
In the first jump from n equals 1 to n equals 3, does it give off light?
Going from n equals 1 to n equals 3, it's actually absorbing a photon. So in this case, it's absorbing light. So this is where you might get that absorption line. It's taking it in. Does that make sense? Any other questions?
Kind of. Just out of curiosity. Obviously, the diagrams that grows over simplification of how things actually work. Like, an electron doesn't actually just so happen to encounter, or a photon doesn't so happen to encounter an electron, right? Like, it's the whole electrons are everywhere thing.
Yes. Yeah. Yeah, so it's not like this electron happened to be in this location and they crashed into each other. Yeah, no, it's substantially more complicated than that. But only certain energies, only photons of certain colors correlating with certain energies can be absorbed by these electrons. So nothing in between. So that's why those lines are discrete. We'll actually talk about that tomorrow, but it has to do with if you look at the wave mechanical model, the fact that only certain waves will resonate depending on the distance from the nucleus. And so it's actually this wave mechanical model that dictates what energy shell those electrons can actually exist in and why they can't exist in between. Okay, somebody was asking about alpha particles a little bit earlier and what they are. So Rutherford was using radioactive decay of the element americium. When that element decays, one of the things that gets released is this alpha particle, and an alpha particle is 2 protons and 2 neutrons. Really, it's a helium nucleus. So a helium nucleus being just a helium atom with its electrons stripped away. So that positive particle would go through the gold foil. I don't exactly know why gold foil was chosen, but I expect it was chosen because it can be made very, very thin. And so you weren't looking at a lot of big layers of nucleuses or nuclei in there. So the thinnest possible layer of metal that could be put there. Okay, so quantum mechanical model. Any other questions?
I just Googled why it's gold foil. Online it just says because
Right, yeah. So that's what it is. Basically, gold's super malleable. And malleable literally means you can hit it with a mallet, smash it with a mallet into thin strips. So yes, I think there's people out there, they'll like eat gold foil, or they'll put gold foil on their food. Maybe President Trump, I'm not sure. But if you're going to eat gold, it's pretty cheap because you can make it really thin.
Yeah, it says it goes around 1,000 atoms thick. So.
Perfect. All right. It's expensive, but it was thin, so that maybe made it cheaper. Okay. That's the Bohr model of the atom. We're on to the quantum mechanical model tomorrow.